This is a video to discuss some of the concepts from section 2.1 in the textbook, which is looking at increasing, decreasing, and piecewise functions. This first slide shows us the objectives, and they're pretty much following in line with what the section is titled. Now, when we think about an increasing function, it makes sense to think that it is rising as we move from left to right or along the x-axis from smaller numbers to larger numbers. We can see that the picture of this graph is rising or increasing. But if we want to have a formal definition that mathematically says that on a particular interval, in a given range, and the interval is given this generic letter I. So we're looking at the x values that are going from here all the way to here. We're only looking at those x values from this point to this point on the x-axis. And within that part of the graph, it is increasing. It may be that the rest of the graph actually decreases on the other side. We're not sure, but just within that given interval, it is increasing. So if we choose any point in that interval, let's call it point A, right here. And if point A is less than point B, these are the x values that we're choosing, f of A, or the y coordinate that's associated, when we plug A into the function, we get its corresponding y value, f of A, meaning it has been plugged into the function, versus b of f of B, where we're taking that number b and we're plugging it into the function, figuring out what its y value is. Anytime that A is less than B, f of A is less than f of B. And we can do that for any different points. We could pick two different points in this interval. We could pick point A to be, say, here, and we could pick point B to be, say, here. F of B is going to be up here, f of A is going to be here. It's still following that same guideline that we have created. And so we say it's increasing in that entire interval as long as we can pick points that are in this format. One thing to notice is that the endpoints are typically not included when we talk about increasing and decreasing intervals. And that is because if I have a function that, let's say, looks like this, it might be increasing from everything over on the left up to this point right here. And then it starts to decrease again. So we've got it increasing here, but then we've got it decreasing over here. At this exact point, that is going to be a maximum point, right? And at the maximum point, it's not increasing or decreasing. So when it changes from increasing to decreasing, it's considered actually to just be constant, completely flat. In fact, as you move forward into calculus, we'll say that there's a tangent line sitting there. Similarly here, this is going to be a minimum point, and it's going to be neither increasing or decreasing there. So anytime that it changes, we don't consider those points to be within the intervals of increasing or decreasing. All right, now, as you would imagine, the definition for decreasing is similar to that of increasing, just going in the reverse. If I take any value in this interval, anywhere from here on the x-axis, anywhere from here all the way up to here, if I pick any 2 points, I'm selecting point A and I'm selecting point B, and I'm plugging them into the function to figure out what their corresponding y values are. F of A is up here, and f of B is here. And I can see that as I go from left to right on the x-axis, the y values are decreasing. And so on this whole interval, the function is decreasing. Similarly to the increasing definition, we don't include the endpoints. This definition seems pretty obvious to all of us. We have come across in the past functions that we would call constant, that they're not changing. If we were to think about this in terms of money that we're making over time, this would be an indication that, say, every month we're making the exact same amount of money. But again, the formal definition involves some form of an interval. And in the interval, if we pick any two values of the x, on the x's a and b, and I plug them into the function, f of a and f of b will be exactly equal to one another. They'll be on the same plane. Now we can have functions that have all three of these increasing, decreasing, and constant intervals on them. For example, we could have a function that was increasing, decreasing, constant for a certain period of time, decreasing again, increasing. As long as we don't have any portion of the graph violating the vertical line test, this is a function and it has different intervals along it that are increasing, decreasing, and constant. In this case, up until this point, we would be increasing. We would also be increasing from here on. We've got a little decreasing part here. We've got decreasing here, and this is constant. As we go into class on Wednesday, we will look at some specific functions and we'll put values on the intervals so that we can have more specific guidelines as to eventually what the domains are. Now, here's an example of a function that has what acts like a minimum. If I look at this point here, it kind of looks like a minimum just if I maybe look at just this part of the graph, right? It looks like a minimum point. But it may be that the graph at some point down here comes further down, and actually there's a minimum point that's lower than that somewhere else in the graph. We don't know. Because we don't know what the rest of the graph looks like, we call it a relative minimum. It acts like a minimum just within its little neighborhood, just right around where it lives. Similarly, this point up here is called a relative maximum. It is a maximum just in the region where it sits. Everything around it has a lower, a lesser y value. But we know it's not a maximum for the entire function because we can see that there are values over here that are higher than that one. So the definitions for relative minimum and relative maximum have to do with looking at a particular interval, right? That if I look at points just in a particular interval, right around that point, maybe just around that point, for a maximum, any value c, for any value c, which is where the maximum sits, any x near it will be below. For the minimum, any x near it will be above. So again, these are just formal definitions we have mathematically, and this is just to get you acclimated with some of the language that we'll be using. Here's an application problem. This is an example at a community college that has dividers, like panels that you could move around to block off a certain area where you wanted to have a testing center. And it says that they have a total of 30 feet and they want to make a rectangle with each of these. Now, some of the problems that you'll work towards in pre-calculus and calculus would be to maximize the space, right? We want to have as large of a space as we can with the given dividers that we have. So we'll learn later how to maximize this problem, find the maximum value, but right now what we'll do is we'll first set up the function, and then we'll look at Desmos to see the graph to find the maximum value just by using a picture. So we're going to say that x is going to be the length of the rectangle. We're not sure how big of a rectangle we're going to make, but let's call this x. And then because we have 30 feet in total, this side will be 30 minus x. It's not stated in this, oh it is, this is a corner of the math lab. So the other two sides here, this side and this side. These are walls, so we don't need to put any dividers there. We're just putting them on the outside. So if I add these two purple sides together, I'm going to get a total of 30 feet. Now we know that the area would be to multiply these two together, and we get this nice function here, 30x minus x squared. If we go ahead and graph that in Desmos, x is going to be the width of the rectangle, and y is going to be the area, the total area, right? Looking back at our function that we had, the variable x was the length or width, right? And I guess they're calling it length, but this is the y value where we're plugging in, where we're plugging the variable x in, and so that's going to be the area. So I'll change this to length. Looking at the graph, we can see that the maximum occurs at 15 to 25. So that means that we'll get a maximum area when we have the length of the rectangle at 15 feet, and then the total area will be 225 square feet. Again, moving forward in calculus, we'll talk about ways to do this algebraically rather than using a graph. The next set of examples are what we call piecewise defined functions. A piecewise function is just a number of functions that we've put together to create a single graph. And what we have listed on the right-hand side here are considered to be the domain, where the function is defined. So if I put all of these values together on, let's say, a number line, the first portion is going from, actually, why don't I do these in different colors? Hang on. Let's do this in yellow. And we'll do this in green. Okay. So we're going from negative infinity up to -2. And we're not including the point -2 in the first portion of this. Hang on, give me a second. So we're going to have blue anywhere the function is going to be less than that -2. Now the middle part of the graph is going to be defined from -2 up to 3. And it's going to include those 2 points. So I'm going to go over the little hash marks there. So yellow is going to include those endpoints. And then the third is going to go from just above 3 on. So the graph x plus 1 is going to be in that first portion. X plus 1 looks, it's a line, right? It looks kind of like this. And then we're going to have the graph 5, that's a constant graph, somewhere in the middle, somewhere like this we'll have a constant graph. And then for the rest of it, we're going to have x squared. The x squared graph looks something like this. If we were to graph this in Desmos and see all of these three together, we could see that the graph is going to have 3 separate components, and they're going to vary based on what the set domains are. We'll look at that in just a second. For this first part, we're just being asked to evaluate what the function value is. So they want us to find f of -5, -3, 0, 4, and 10. We don't take those values and plug them in 3 times for each of the functions that we see. We use the specified domain that's given to us. So for the first one, for f of -5, we're going to use the first part of the graph, the blue part, because -5 falls within that domain of being a value that's less than -2. So, let me scroll up here for a sec. F of -5 is going to be, we're using the first function, it's going to be negative 5 plus 1. We're using the x plus 1 portion. So our answer there, the value will be negative 4. For f of negative 3, we're also still in that same function. So we'll use negative 3 plus 1, or x plus 1, and we'll get negative 2 for our output. This means that some of the points on the graph are negative 5, negative 4, and negative 3, negative 2. When we want to look at f of 0, 0 is going to be in that middle part of the graph, right? It falls in between negative 2 and 0. So instead, we're going to use this function output. It doesn't matter what value you are for x, if it's in between negative 2 and 3, the output value is going to be 5. So another point on the graph is 0, 5. The last two values, 4 and 10, fall within that last portion of the domain because they're both greater than 3. So f of 4, we're going to use the x squared, so we'll take 4 squared, which is 16. So 4, 16 is a point on the graph. And for f of 10, we'll look at 10 squared. And so we have 10, 100 is a point on the graph. All right, let's look at Desmos for just a second. So I've brought up a Desmos graph, and there are 3 different portions of the graph. I need to type in y equals here. So by looking at this, they're all overlapping one another, and so this wouldn't be a function in the way that I have it written because it wouldn't pass the vertical line test. We've got multiple y values for any given x input. In Desmos, you can specify the domain the way it was in the original by using curly brackets. So for the first portion, we wanted x values that were less than negative 2. So I'll type that in there, and so you see that it restricts that line. It only has that, it has that line end at negative 2. For the second graph, we're going to have y go between negative 2 and 3. And then, hang on, does it do that? I want it to be, sorry, negative 2 less than or equal to x less than or equal to 3. There we go. So it cut that graph into just a small portion. And then the last part for the x squared, that is x greater than 3. All right, let me zoom out a little bit here. And then we can see we have 3 portions of the graph. They don't intersect one another. The only thing with Desmos is it's not going to show you the open circles and the closed circles, right? But we know that anywhere that there's a strict inequality, we have an open circle, and anywhere that there's an less than or equal to, then there is a closed circle. All right, let's go back to OneNote. Here's a different example of a piecewise function. It's broken up into 2 separate portions of the graph. 1/3 x plus 3 is a straight line, and that graph is defined only for x values that are less than 3. So we can see that when x is equal to 3, that's where the graph is cutting off. There's an open circle because there is no equal sign. It's a strict inequality. Now, the other portion of the graph is for everything where x is greater than or equal to 3. So that's the second part of the graph. It's negative x as the function. But because of the equality sign here in the domain, we have a closed circle. That part, the value 3 is included in the second part of the graph. The thing that we want to take note of is that when we draw a line here, there's only one place where the function is defined. The vertical line test says that anytime we draw a vertical line, there can only be one y value. The y value is right here. The y value for this second green line is right here. The one up on top is not included because it has an open circle. So this still passes the vertical line test, and it is a function. Here's another example that is a little bit more complex, where we have what's called a hole discontinuity. At first glance, it looks as though the graph is just a straight line, but there's one place where the graph is undefined. Anytime we have a fraction or a rational function, we are not allowed to have the denominator equal 0. So in this case, we cannot have x equal to -2 because that would cause us problems down in the denominator. So -2 is going to have, there's going to be a hole in the graph at that point. The function is undefined there. In this case, we wanted to redefine the function somewhere else. So we just said, okay, well at that one little point, when x is -2, let's have the output value, the y value, be equal to 3. And so we have this little point that's up here on the top. This will be particularly important as we move towards calculus because there is this concept called the derivative, which is looking at the slope of a line and how things are changing over time. And we have to proceed with caution any time that there's a hole in the graph. And there was another example I want to go back to real quickly. Oh, it was right here where we have this little thing that's called a cusp. A cusp is when you have, it's not a corner. A corner would be where you have two straight lines together, like in the absolute value graph. Sorry, not writing very well. Corner. A cusp is when you have either a straight line and a curve, or in this case, two curves that meet in this sort of corner. And that is something that causes a problem for us in calculus as well, because we can't take the derivative at those points. So thanks for watching. I hope you were able to get just some of the terminology that we'll be using. And if you have questions, you can send me an email. Have a great day.